First of all, thank you for coming. It's preposterous that you're here, but thank you for coming. The man who coordinated my GSci 20 labs, Dr. G. Michael Clark, who got his doctorate with me subsequently, is in the audience. And in the construction of that tape, I would like you to know that most of the tape was actual work, but it was 3 hours long. And about every 40 minutes, we take a 2 or 3 minute break to let the student relax. All my friend played was the relaxation part of the tape. Nothing to do with the working part of the tape, which is how to tell rocks and minerals, etc. And Mike coordinated the effort. When Terry called me up and he said, "Would you like to give a lecture at Penn State?" my initial reaction is, this is some kind of a Halloween joke. But it wasn't, and I said, "Well, what did you want me to lecture on? The geology of the Gatesburg Dolomite?" Or no, the geology of some place in New Mexico that I've been lately? No. Is there any particular lecture people liked? I said, "Well, I don't know, but I know one that they seem to stay awake for." And that, let me set the framework of this whole thing for you, please. GSci 20 was a course aimed at people who are not science majors. They were humanists, liberal artists, business BBA people, journalists and the like, agriculture. They were people who were taking this course to gain some insight into science, which is so important part of their life. Subsequently to 1970, science manifested itself in such things as iPods and cell phones and has come into your life never to depart. Now, I therefore decided I ought to give some lecture to explain to the non-scientist where science came from and what it was. In preparation for this, I passed out a piece of paper in 1957 or so, asking people to tell me what science was. And I got, in many cases, the usual answer: science is organized knowledge, which places the telephone directory and the dictionary at the top of the scientific pile. I said, "No, that's an insufficient designation." Then I had some other students for whom hope springs eternal that said, "Science finds the truth." Oh, no. If you can find the truth, you're more than a scientist, I assure you. We try and find what is better estimate of the truth than the previous one. So I decided to give this lecture on the development and evolution of scientific thought. Now, in 50 minutes, it's pretty presumptuous to try and talk about the evolution of science. So you got to restrict yourself. To wit, Western science, because we know very little about the evolution of science in the Orient. We're learning more about it now as history digs into it, but mostly it's Western science. And you have to pick one thread, otherwise you can't do it. So the thread I picked was physics, because it's a very fundamental science and underlies many of the others. Okay, so what do you start off with? You start off with the pre-Socratic philosophers, because anything worthwhile in the West had its inception, whether you like it or not, in ancient Athens and its forebears. That's where it came from. They were very smart people. They didn't sink ships in those days. Nasty remark. Okay. The pre-Socratic philosophers came up with an extraordinary idea. They said it is possible for human beings to examine, study, and explain. Now understand, please, any time an event occurred which couldn't be easily explained, it was attributed to the gods. The god Neptune did this, Pluto did that, Zeus threw a thunderbolt, what have you. They had a lot of gods. Some people streamlined this and had only one God who did the miracle works, but the explanations were always divine. In fact, in the Greek play, the Deus ex machina came down and did it for you if you had a problem, made it go away. That no attempt to explain it, no attempt to understand it. This great concept was, instead of attributing it to the gods, let's study it and see if we can understand it. Let's form a hypothesis about it, a theory to explain it. Then came the Socratic philosopher, Socrates himself and his great student Plato. And they began to formalize the way you did this. You just didn't look at it and say, okay, this is the explanation. You used a very powerful tool of the human mind called logic in order to deduce what it was that you were trying to explain. You could deduce your theorem from the observation and data, and you followed very rigorous logical being. Aristotle, one of the giants of Greek philosophy, developed, for example, a technique. They understood deductive and inductive. He worked up the syllogism, a very, very powerful tool of logic. If you misuse it, you come up with some funny results. The first time I ever had a syllogism, it was pointed out to me that if you're not careful, you come up with things like man is an animal, a horse is an animal, therefore man is a horse. That's not good logic, although it follows the form of the syllogism. There are very strict, rigorous rules. All the time the philosophers were laying down this method of attacking problems and trying to come up with an explanation. Underneath them, the substrate was being laid by the mathematicians. The first well-developed branch of mathematics, really, in the West was geometry. Geometry was caused by the fact, as you all remember, the Nile periodically flooded. Everybody lost their property boundaries, and they wanted their property back. And if you had a few points you could triangulate in on, you could redivide the property the way it was. Geometry. In Alexandria, the intellectual capital of northeastern, what is now Egypt, northeastern Africa, populated by Greeks, they developed some wonderful mathematics. There was a chap named Euclid. Everything logically deduced, the 5 postulates. He could only prove 4 of them. And the fact that he didn't prove the 5th came back to haunt everybody in 1850, but I'll come to that. He had these postulates of geometry, and very logic. You all remember the axioms of Euclid, such common sense things as the whole is the sum of its parts, maybe? No. Yeah, okay. Now, in addition, some of the science that was done was extraordinary. The librarian of the Library of Alexandria, one of the great wonders of the ancient world, I'll mispronounce this, was a man named Eratosthenes or Erasthenes, and he did a very wonderful thing. He got himself a sand glass so he could measure time, and he stood at one well and waited till the sun shone completely in the well, meaning it was directly overhead. Then he waved signal flags, which were quickly passed. The sand glass was turned over, and they waited till it got to another well whose distance away they knew exactly located. They knew the exact time it took the sun to move an exact distance. And then, because they hadn't yet learned that the world was flat, they knew that this sun was going to do it in 24, or what we today call hours. He calculated the circumference of the Earth at the latitude of Alexandria, and he was off by about 150 miles, which ain't bad. You could almost get an NSF grant to refine that. That's an extraordinary piece of science and way in advance of anything that was done for over 1,000 years. It was buried. It was lost. It's not the first time great ideas, scientific and otherwise, have been buried. The great giant of Greek science, however, by far, the greatest scientific mind of antiquity, was a man named Archimedes, who lived in the town of Syracuse in Sicily. He's the one, you know, who was in the bath and was asked to determine whether the crown was mixed with lead or whether it was pure gold. He understood, he jumped to Archimedes' principle, and supposedly he ran through the streets of Syracuse yelling, "Eureka! I found it!" After which they named the vacuum cleaner. He was an extraordinary individual. He understood the principle of the lever, the mechanical advantage, the arm times the force equal the arm times the force. He understood the mechanical advantage of the screw, that you could raise great weights by lifting them with the screw. He understood pulleys and the mechanical advantage of pulleys. Finally, in the early 200s, the Roman general Marcellus descended upon Syracuse to capture it and make it a Roman colony. and the Roman triremes came up to the walls of Syracuse. And Archimedes had been asked by the king of Syracuse, Dionysius, please help us defend the city, O great and wise scientist. And he did. Using the pulleys, he was able to pull down catapults of much greater strength than any others, and they hurled rocks, which Livy, the Roman historian, describes, you can guess they were about 200 pounds, with such accuracy that they sank the Roman ships. He then reached over the walls of Syracuse with grappling hooks on a lever, and then with the mechanical advantage of the lever, picked the ship up, shook it till the infantry fell out of it, and let it drop. This caused the Romans consternation. In fact, Livy says the last time the Roman ships approached the walls, this is true, you can read it, came up to the walls, he said an old man leaned over the wall with a piece of rope and shook it, and the Roman ships took off. They'd had it. Well, the Romans conquered Syracuse the way they usually did, by treason. They found themselves a traitor. They bought information about a pass through the mountains on the land side of Syracuse. They arrived in the city through the pass on the night of the Feast of Bacchus, when half the citizens of Syracuse are lying drunk in the streets. And Marcellus turns to his commanders and he said, turn them loose, anything they want, pillage, rape, but I don't want you to touch Archimedes, bring him to me. I want him on our side. Have you ever heard of Peenemünde and the German rocket station after World War II? When the Americans and the Russians said, let me at those German rocket scientists. I want the people who designed the V2 on our side. Yeah, no difference. That's exactly what the Romans did with Archimedes. He didn't have a V2, but what he had looked like the V2 to them. And the story, according to Livy, is this Roman soldier came marching up, found this old man drawing circles and triangles in the sand, and he said, are you Archimedes? And the old man said, just a second, I'm working on the proof here. Yeah, Marcellus wants you, just a moment. And he killed him. The death of the first egghead. And I used to tell the class that evidence is not quite complete that the Roman soldier's name was Josephus McCarthyensis. But in fact, we don't know this. With the death of Archimedes, really, ancient science as we know it, science, math, physics, and understanding of mechanical things, stopped. The Romans took over, but the glory that was Greece faded in the rise of the Roman sun, as the historians like to put it. And the Romans were superb engineers. They built aqueducts that still stand. You can see the arches. They built a sewage system that still works sometimes in modern Rome. They built a wonderful water supply system that brought water to this large city on 7 hills. They built the Colosseum, which is a marvel of engineering and architecture. They were superb engineers and builders, and they were superb military people. Obviously, they conquered the known world in the West at that time. They were wonderful organizers and legal. We still live under Roman law, or its extension today, except for Louisiana, which lives under Napoleonic law. That's another problem. But anyhow, and New Jersey lives under Roman law. The fact is that Rome did not advance theoretical science, but it did advance, indeed, applied technology. Eventually, of course, Rome fell from internal as well as external forces. The Ostrogoths, the Visigoths, the Huns swept down over the city. Eventually, in around the middle 400 AD, they conquered Rome and sacked the city and destroyed it. And with the death of Rome as a Western empire, the Eastern Roman or Byzantine Empire, based in Constantinople, stayed on. But the Western Roman Empire fell, was scattered, and what we are pleased to call in our pomp the Dark Ages settled over Europe. No place else, over Europe. And the 5th century, not much, 6th century. Then in the 600s, we had the flight of Muhammad from Mecca, the founding of Islam, the Hijra, and the Saracens, who were the Arabs, swept across North Africa into Spain, where they were known as the Moors, and up the Spanish peninsula, until they were finally stopped in one of the pivotal battles of European history, the Battle of Tours by Charles Martel. Now, the Moors or Saracens, interesting. They had Europe on the left side, if you look at a map, and on the eastern side, they were in contact with India. And from India, they learned a few things. One of the most wonderful things they learned from the Hindu mathematicians was the decimal system. Ladies and gentlemen, would you like to multiply 4.702 by the square root of 3 in Roman numerals? As the great, great mathematician Gauss said, if only Archimedes had invented the decimal system, science would be 2 centuries ahead of what it is today. But the Saracens brought the numbers, the decimal system, all the way over to Europe. We got it from the Arabs. To this day, we call them Arabic numerals. It's a misnomer. They should be called Hindi numerals. But that's the way history goes. Did they bring anything else from India? Yeah. They said, you know, it's possible to write an equation that has an unknown in it, which we'll call x, and we'll solve for that. It has an Arab name. The Arab word is algebra. And it's still Arab to some students in high school. But algebra came with the Saracens, and it came from India. There was a great deal of other information that came. Medicine advanced very greatly. In fact, in the 10 and 1100s, if European nobility and the aristocracy, where money was no object, got ill, they went to Egypt to be treated by a man whose name was Moses Maimonides in English, who was a rabbi and a Hebrew scholar and the physician to the Khalifa. And he treated people using medical techniques of herbs and what have you, which are not too far off. They knew, for example, that if you had chills and fever, you chewed the plant foxglove, from which we eventually isolated quinine, which is a specific in the treatment of malaria. But the Dark Ages still persisted because if you went back and said, like the Greeks, I would like to explain this miracle by logic, you ran into trouble because that miracle was due to the intervention, for example, of the Archangel Michael. And if you don't like that, you're in trouble. But I just want to, if you are, you see that stake? You see the bunch of twigs at the bottom? You don't really want to study that. Words to that effect. And so darkness settled over science. There was no science. There was such things as how many angels dance on the head of a pin. You said, no, that's a story. No, it's actually true. There is a learned discussion, of course in Latin, as to how many angels dance on the head of a pin. And I always point this out as poor science, because nowhere in the article do they specify the size of the pinhead. That's poor. Okay. Then the light begins to break. Without spending a lot of time, you're all well aware of the Renaissance. The word means rebirth, which was the discovery of the ancient Greeks by the scholars in Europe. That's what the Renaissance wasn't Italian. It was the discovery of ancient Greeks. Now, the Italians happened to be in on the act very early. One of the first things that happened is a chap by the name of Copernicus came up with a novel idea which he was afraid to publish in his lifetime, but it was published posthumously, that the sun, not the earth, was the center of the solar system, or at the center. Because the earth, which is our place and which was built in 6-7 days, it had to be the center of everything. He said, no, the motion of the planets doesn't make sense if you make the earth the center. The planets do things like this. Well, how do you account for that? Well, you have epicycles. Upon epicycles, 4 levels of epicycles to explain all this crazy motion. If you put the sun in the center, everything is just perfectly smooth. In fact, a Dane named Tycho Brahe, using probably the first National Science Grant from Copenhagen, an enormous amount of information, great amount of data, of measurements of planetary motion. Nobody could make a lot of sense out of this until a very patient man named Johann Kepler beat this data to pieces for years and years and years and finally came up with basic laws of planetary motion. The planets describe an ellipse and the sun is one of the foci ellipse. radius vectors, the arms sweep out equal areas in equal time, and all kinds of wonderful math. He did that for 28 years. That calculation today on a simple PC takes 25 seconds. It's a pitiful waste. He didn't have a computer. On the other hand, he accomplished, and he was happy. Today we have the computer, maybe we're not so happy. But anyhow, these are wonderful ideas. A real genius in this group, and one of my favorite little nasty people was an Italian named Galileo Galilei. He was a fighter, a scrappy little rascal. He was wonderful. He did many, many things, but the stuff that he did that was really great, we don't pay much attention to. Let me give you what kind of scientist this guy was. He was in a great cathedral in Florence, because he lived in Florence, and it was open, there was a wind, and the chandeliers were swinging. And the chandeliers were a different length, and the swinging arc was of different length. And he sat there bored stiff with the sermon and the homily, of course, and he used his pulse to time the swing and deduce the law of the pendulum relating the arc swing to the length, just the way we set a clock. And the law of the pendulum he got from using his pulse. Now I thought to myself, he must have been a very calm man, because if he got excited, the pulse would go up and the data would be useless. So he was really calm. He just sat there, oh, sir, what the heck do you know about that? Beautiful. He also came up with some other wonderful ideas. He said, be awfully careful of what is obvious, what is so logical, it doesn't need any further explanation. For example, here is a weight in space, and it's fixed, no friction. The physicists love frictionless. And you push on it, it goes faster, right? Yes. And if you push on it less hard, it goes more slowly, right? Yes. Therefore, force is proportional to velocity, right? Wrong. Wrong? Yes. What's proportional to force is acceleration or change of velocity, said Galileo, not velocity. But it's intuitively obvious. I don't care if it's intuitively obvious, it's wrong. My God, a shattering thought was picked up by René Descartes and Francis Bacon. They said, you know, using pure logic to deduce very carefully from the data an explanation is insufficient. We must test whether the explanation is correct. That had never been done before. And they said, okay, what we do is come up with our theory from the data. Based on that theory, we make a prediction and go check the prediction. If it's right, then the theory's right. If it's wrong, throw the theory away no matter how much you love it. As they say, practice infanticide on your own brainchild. Get rid of your pet theory. Oh, and if you could make 5 or 6 predictions, wow. What they didn't know, but what was coming later, is if you want to make a really valid prediction, try and express it mathematically. Then instead of saying, if my theory's right, this should be bigger, you can say, if my theory's right, this should be 4.23 times bigger, and go check it. Mathematically, you can get a much tighter check on your prediction. So now we have 4 steps which constitute the scientific method. Gather the data, unbiased data. If the data's biased, then you get what are called political analysis. Or politicians. Political science is valid, but some of it is not well done, which is true of a lot of things. Okay, you gather the data. You come up with an explanation for that data, preferably, if you can, couch it in mathematical terms. From that, you make a prediction. If my theory's right and this happened, then this should occur, the cause and result, and check it and see if it works. If it does, this is a working theory. If it doesn't, back to the drawing board. This was the work of a man named Francis Bacon, who was a philosopher, a modest guy who said, I take all knowledge to be my province. It was a great statement. And he did in that time, because all knowledge would fit into his pocket. And René Descartes. I love the story of Descartes. You know the great joke about René Descartes? Break. He walks into a store, looks at a book, and the bookseller says, Monsieur Descartes, what do you think of that book? And Descartes says, I don't think, and vanishes. Remember, he's the one who said, I think, therefore I am. If he doesn't think, he ain't. I like it. Old Descartes. Anyhow, Galileo did wonderful things. He also did something else which snuck by and didn't come out till many years later. He said, you know, when we talk about a body moving or in a state of rest, we had better specify the coordinate system we're using to measure it, or we're going to have problems with relative motion. Example he gave was, you are standing on a moving ship. As far as the ship is concerned, you ain't moving. But to someone standing on the shore, you and the ship are both moving. So it's the relative position of the observer and the coordinate system. And he used the term relativity. Now, it's not the same as Einsteinian, but it makes the hair on the back of your neck stand up when you read this, which came out in 1620-something or other. He died in 1641, and as so often happens in science, people, the time was ripe. Everything was ready for a great genius or integrator to come along and put the whole thing together in a working system. And this man was an Englishman, of course, named Isaac Newton, who was born in 1642. When Newton was born, he was so small, his mother told him that he fitted into a quart mug. How am I doing on time? Because I'm only up to 1642.
20 minutes.
20 minutes? That's 10 minutes for the 18th century? Okay. Newton was, of course, a monumental genius. He was a brilliant experimental physicist. He was one of the three greatest mathematicians who ever lived, Archimedes, Newton, and Gauss. And he was also a weirdo as a person. He was just a terrible person, but who cares? Nobody cares that he was nasty. They cared what he did. And what he did was, before he was 24, invent the differential and integral calculus independently of a German named Gottfried Wilhelm Leibniz, who did the same thing. He developed the three laws of motion, Newtonian laws, precisely stated. A body at rest tends to stay at rest, or a body in motion tends to move in the line of vector force, blah, blah, blah. Every force has an equal and opposite reaction. That's why our rockets go up, etc. I'll go into a lecture on Newtonian physics. Very, very brilliant. And he made a bunch of predictions, because until he made the predictions, they said, that's a very nice theory you have, Mr. Newton, but who cares? So he made predictions. He predicted the tides from the pull of the moon, and he was within an inch and within a minute of time and distance. Oh, wow. He predicted other things without going. His predictions were right on the money. We had solved the riddle of the God's head. It takes the poets, of course, to go off into the wild blue yonder. Poet, Wordsworth, statement. Nature and nature's laws lay hid in night. God said, let Newton be, and all was light. Pretty nice statement. But that's not a scientist who made that statement. It's a poet, and it rhymes, but it isn't right. Okay. It's true, isn't it? Yeah, okay. So Newton advanced these ideas, and we took off. We had solved the riddle of the God's head, as they put it. Without going into long stories, mathematics, using the calculus as its base, what Feynman calls the language of the universe, took off. Unfortunately, the English stuck with the geometry Newton used in his great book, The Principia. In continent, they went the calculus route. Great mathematicians, Leonhard, Euler, and others in the early 1700s into the late 1700s. And finally, in the late 1700s, we reached a crescendo of excellence in science. One, geology became a science, and therefore Terry and I could make a living. There is a man by the name of Hutton talked about what he called uniformitarianism. Before that time, since the Earth was only 6,000 years old, everything had to occur cataclysmic. Valleys opened by great cataclysmic, catastrophic, the catastrophic theory. Because why was the Earth only 6,000 years old? We knew when Jesus was born, and then if you look in the Old Testament, you got the begats, begat so-and-so, begat so-and-so, begat so-and-so, begat so-and-so, and for some reason they figured it was 25 years per begat. And you go back, and then days of this and 40, anyhow, Bishop Berkeley came out with 6,006 years. Okay. Hutton said, no, the Earth is a lot older. If you read his book, it's kind of a shock. He said the Earth is as much as 100,000 years old. Oh, yeah. And he had, therefore, what he called the principle of uniformitarianism. The present is the key to the past. We look at the present. These are the same forces that act in the past. We can work out the Earth's history. He wrote in such an obscure, heavy-handed way that nobody understood what he was saying, but he had a man named John Playfair, who was kind of an interesting guy in other ways, who put the whole thing into simple English, and it became accepted. At the same time, a Frenchman named Lavoisier took the phlogiston theory, which was absolute nonsense, and debunked it, and laid the foundation for chemistry, modern chemistry. He's considered the father of chemistry. And the revolution cut off his head. And they said to Robespierre, France has no need of savants, said Robespierre. And of course, 2 years later, guess whose head rolled from the guillotine? Voltaire, right. Not Voltaire, Robespierre. Yeah. Poor Voltaire was an entirely different thing. I love him. Voltaire was very funny. He fled France, rented a castle over in Switzerland, and all his friends came and freeloaded on him because they wanted to listen to the great Voltaire. And he said, what is the difference between me and Don Quixote and my friends? Don Quixote mistook a palace for a chateau. My friends mistake my chateau for a palace. But okay. More important than that, the crowning achievement of Newtonian physics was the work of an Englishman and a Frenchman named Adams and Leverrier. The furthest out known planet then was Uranus. The purists hadn't worried about whether it was a planet or not. And Uranus had an eccentricity in its orbit. It didn't quite fit the Newtonian projection. Well, normally, if it doesn't fit the theoretical projection, something wrong with the theory. But we were so sure we were right, they said, no, something's wrong with Uranus. The theory is right. And sure enough, they did a calculation. They say everything can be explained if there's another planet of such and such size out beyond Uranus. We will call it sight unseen Neptune. And they put the telescope on the sky at that time and that place, and guess what appeared right on schedule? Neptune. Wow! If you want a proof of a theory, you prove something that nobody even knew was there, and it shows up on schedule. Wahoo! In 1800, we owned it all. Science had solved the riddle. And then the roof fell in. They began to study funny things. Oh, yeah, one final thing I love. There was a famous mathematician, there were several great, Lagrange and others, named Laplace, Marquis de Laplace. He wrote a book called the Mécanique Céleste, the Celestial Mechanics, in which using differential equations, he'd worked out the motion of the celestial bodies. He presented a copy of this book, of the motion of celestial bodies, to the Emperor Napoleon, who was not a very good mathematician. And Napoleon apparently glanced at it and said, Monsieur le Marquis, I see no mention here of the Almighty. And Laplace said, oh, my Emperor, I had no need of that hypothesis. That is science in full an unhappy cry, but that's beside the point. Okay. Then we began to study magnetism and electricity. They made Ørsted, Henry, Faraday. They made wonderful discovery. If you hold a magnet here and you run a wire through it, a current will flow in the wire. What's more, if you put a wire there and pass a current through it, the wire will move. There was a relationship between motion, electromagnetic field, and electricity. The only problem was that you could tell those motions this way. The magnetic field was one way, the wire was another way, and the motion was this way. But wait a minute. Newton said if you push something, it moves in the direction of the applied force, and this was moving at 90 degrees to the applied force. Oh, my gosh. You mean, well, we'll figure it out, that somehow or other it'll fit. Well, it didn't fit. Electricity didn't fit. It didn't fit Newtonian physics, the corpuscular theories. So we had to backtrack a little bit and eat a little humble pie. At this time, once we had challenged that, we had the guts, and I'm coming close, hang on, the guts to challenge a lot of things. A Russian named Lobachevsky and a Hungarian named Bolyai working independently. It so happens so often that occurs two separate places because the time is ripe. Said, you know, Euclid's fifth postulate says if this is a line and this is a point, there is only one line through that point parallel to this line. You put a triangle in there, it shows that the three angles of a triangle are 180 degrees. Suppose, in fact, this line meets at infinity, or meets infinity. Can you construct a system of geometry that's internally coherent that does not include the parallel line theory of Euclid? Yes, you can. It's called non-Euclidean geometry. It deals with funny bent and warped space. Was it important? Einstein needed it later, about 80 years later, for the general theory of relativity. But it was prepared in the 1840s and ready and waiting. In the 1850, to step out of physics for a second, this darned little man in England said, I don't believe in Lamarck. What was Lamarck's idea? How do we get species? Yeah, biology, Linnaean system about the same time. How do we do it? It's very simple. These, let's say a bat goes into a cave, it's dark, it doesn't use its eyes atrophy. After a while we have blind bats. This is called the inheritance of acquired characteristics. Changes after birth are passed on. No, said Darwin, changes after birth are not passed on. There are random changes, mutations within the gene pool. He didn't call it that because he didn't know about it, but there are changes, and then natural selection picks those which will survive. And we had the concept of organic evolution. Everything was fine until he made a bad statement. He said, included in this descent is man. Ooh. That brought, of course, fury down on him. They spied on him because he must be evil. He must practice witchcraft. He must be a Satanist. He was a gentle old man who played with his grandchildren and went to church. They couldn't find anything wrong with him, and the theory survived the attack. Then in the 1860s and 70s came a major break. A wonderful, wonderful man who was not given enough credit, a Scotsman by the name of James Clerk Maxwell, who was a brilliant mathematician and physicist, began to study electromagnetic fields. He studied electricity, he studied magnetism, he studied the relationship, came up with something interesting. The ratio of their velocities was the velocity of light, c. What is there about the velocity of light? I don't know, but there's a constant c in physics, which is the velocity of light, but unimportant to that, it is a constant which appears again and again and again in physics, got nothing to do with light, but it's equal to the velocity of light. And he said, wait a minute, this light, therefore, is an electromagnetic phenomenon, it's an undulating wave, and light moves through space, therefore, electromagnetic field should move space, and it's only part of it, so there must be parts of the electromagnetic spectrum of higher frequency and lower frequency, different wavelengths, which could propagate through space. I predict that electromagnetic fields can be propagated through space. And 13 years later, Heinrich Hertz sent the first radio wave through space, 1888. In 1901, Marconi sat in Newfoundland and got a wireless signal from Wales. And now we can turn on a TV set and listen to political ads because electromagnetic fields. Maxwell, you fool. No. Maxwell's brilliant insight into the propagation of the electromagnetic field opened a whole different set of things. Then two Americans, Michelson and Morley, did a wonderful experiment. It's famous, the Michelson-Morley experiment. What is it? They measured the speed of light with an interferometer very accurately. What did they discover? That no matter what direction light traveled, the speed was always the same. The speed was independent of direction. So what? Well, wait a minute, you Newtonian character. If you're riding on a train and you throw a ball, the speed of that ball is the sum of the speed of your arm plus the speed of the train. If you throw it the other way, it's the speed of your arm minus the speed of the train. So it matters which way you throw the ball. But if it's a beam of light, the velocity is exactly the same regardless of the moving system beneath it. Is this remarkable? Ah, it's astounding. There's something else which I hesitate to do because in my youth I could do it, and young anymore I am not. They developed statistical mechanics, the work of Boltzmann and others, and America's probably greatest theoretical physicist was instrumental in this, a man named Josiah Willard Gibbs, did many other things. You take two gases. This is a hot gas, so the molecule has a lot of energy. This is a cold gas. The molecule is barely making it. So the two hit, and heat will move from the hot body to the cold body. This will speed up, this will slow down, and they'll finally be doing this. But suppose with a certain probability, the hot molecule is at the end of its motion and the cold molecule hits it, energy is transferred from the cold to the hot. So there is a certain probability that things won't go the way they normally should go. And this is called statistical mechanics, and you stick it in there, and you come up with almost the right answer for the final temperature. What do you mean almost the right answer? It's not the right answer. And Boltzmann said, what's going on? And they got another idea, very genius. They said the reason is we're assuming energy to be a continuum, but it actually moves in certain quanta, and you can't get below that. And if you take these quanta of energy and break it up, then you get the right answer. Quantum physics. Woo. Meanwhile, in Germany, a very bright guy was born in Ulm. His name was Albert Einstein. He showed very good promise. He got this is true, he got a B in mathematics in his first, what we would call a B, and his teacher said, "Work harder, Albert." And I guess he did. Because he came up with the following interesting idea. He said, look, let's think about this for a second. Electromagnetic field, that's what we're talking about. Everything is fine, and we have light traveling, but now if the system gets faster and faster and faster and moves it, light is still the same. How do we account for that? How can we keep the velocity of light constant when the system is moving at speed? The answer, he said, is very simple. Time slows down. In other words, what we used to cover in a second, we now have a big second so we can cover more distance so light can go faster. If we're going this way and light should slow down, it slows down the time, and therefore it covers the same distance. And it's wonderful. By changing the time, or we can take the length of a steel bar or a beam of light and shorten it in the direction of travel. By changing the length and the time with speed, as you approach the speed of light, you can keep the speed of light constant no matter how the system moves. And therefore, you could explain the Michelson-Morley result. And everybody said, that's very nice, Albert. That's a theory. What is the proof? Well, he did some more calculations, and he came up with, and we'll go into it, what is unquestionably the most famous equation in the 20th century, E = mc squared. What he found was mass and energy are related to each other, and again, that velocity of light comes in. Got nothing to do with light. It's the value, here, in this case, squared. He made a prediction that if we can, that constancy of energy and constancy of mass, which were absolute shibboleths of science, were wrong. Oh, my God. What about gravity? I hadn't said anything about gravity. Well, you got to talk about gravity. That's a major force. Back to the drawing board. In 1910, he came away from the drawing and said, I got it. I'm going to call this the general theory of relativity. One of the problems with Newtonian physics is I'm exerting a gravitational pull on this gentleman, and he on me. Now, fortunately, both of us haven't eaten too much, so we're small enough not to move each other. But what is the connection between the two of us? How do I exert a pull on this man? How do I get a force acting at a distance? How does the Earth reach out and hold the moon? How does the sun hold? What is the connection? There isn't any. Einstein said there isn't supposed to be. The presence of a large body, or any body, but a large body you can measure, warps the time-space continuum so that objects are turned into, for example, as you approach the sun, it has warped the time-space continuum, and you slide down that slope toward the sun. Let's say you can see past the sun. When? In an eclipse. Oh, And there's a star on the far side. As the sun approaches that, the light from that star should bend around the sun as it's deflected in the space-time bend. And we should see the star make a sudden erratic movement as the sun goes by. And we can do that during an eclipse. And I calculated to be 0.63 seconds of arc. Not very much. In 1917, at the height of World War I, they sent an expedition down to the South Pacific where there was a total eclipse, and they put their telescopes on it, and the star deflected just about what Einstein said it would. Wow. We now understood gravity. We think. We don't, but we thought we did. In 1921, it's kind of interesting, Einstein got the Nobel Prize. For the special theory of relativity? No. For the general theory of relativity? No. For general contributions to physics? Yes. And he understood and explained the photoelectric effect. What's that? If light energy falls on a conductor, electrons come off it. Is this important? Yeah, that's what we're trying to do with solar power. We're trying to generate electricity by solar power. Einstein explained that phenomenon. That's what he got the Nobel Prize for. The people in Sweden sometimes have funny ideas. Okay. In 1936-37, two Germans working in Germany, Hahn and Strassmann, bombarded uranium with neutrons, and in the debris of the wrecked uranium atoms, they expected to find radium atoms, slight changes because energy was given off. They looked and they didn't find radium. They couldn't figure out what they found. They finally realized it was barium. Barium from bombarding uranium? Barium is much smaller than uranium. What happened? So they got a hold of a very, very, very bright woman named Lise Meitner, who had fled Germany because although she was now Protestant, she'd been born Jewish. She saw the gas chambers coming and bugged out to Sweden. They went up there and met her in Copenhagen. They said, Lisa, what's the story? She said, look, when you hit it with neutrons, the uranium atom began to vibrate badly, and it broke into two. And she coined the term. She called it nuclear fission. She said, you have split the atom. No. Yes. Go back and do it again. So they went back and they did it again, and it was true. Now, Lise Meitner got a little scared. She said, if they do that and there's a change of mass, and this thing is self-generating, a chain reaction, they've got a horrendous explosive material with an enormous release of energy. So she went to her friend Niels Bohr, and she said, Niels, this is what's going on in Germany. Niels said, I understand, because it was his model of the atom she used. He came over to the United States and got a hold of a guy named Leo Szilard. He said, Leo, the Germans are working on probably an atomic weapon. They have split the atom, Hahn and Strassmann, blah, 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 blah. My God, Leo came from Hungary and said, what are we going to do? He said, I tell you, we've got to get this information to the Americans. So you write a letter to the White House and sign it by some guy named Leo Szilard, and some secretary says, who's this? And cites a letter saying, the president thanks you for your interest in the national security. Go away and don't buy. Thank you very much, Mr. Szilard. He said, no. We got to get somebody who they will pay attention to. So who do you think they went to get, of course? Albert Einstein. They went to Einstein and said, Albert, look at this. I said, oh, my God. Yeah. And Leo, God, he must have been a cocky individual, said, I'll write the letter for you, Albert, if you sign it. That takes a certain amount of gall. Okay, Einstein said, go ahead and write it. He wrote it. Einstein edited it. Sent it. It's a lovely letter. It's just addressed F.D. Roosevelt, the President of the White House, Washington, D.C., Sir. And then it goes and lays it all out, including an interesting statement. It says, this bomb will be so big that no aircraft can carry it, so it'll have to be delivered by ship. We'll sail into the harbor and blow it up. There was no B-29 at the time. This was 1939. The letter got to Roosevelt because it bore the signature Albert Einstein. And Roosevelt said, look into this. And they looked into it and said, and they formed something called the Manhattan District. And the rest is history. They assembled a mass of brains in a place called Los Alamos. If you've never been there, it was picked by Oppenheimer because that's where he'd gone to scout camp. And it was put there so nobody could find it, and you still can't find it. And it was just a wonderful thing. They had the work of a great and brilliant Italian. They said, look, we want to see if this thing will actually self-generate and go chain reaction. We'll give you an area here under Stagg Stadium at the University of Chicago. Dr. Fermi put this thing together and see what happens. You all know the story. The pile went critical, and they sent the famous code message to Washington about Fermi. The Italian navigator has landed. That meant the thing had gone critical. And indeed, in July 1945, near Alamogordo, New Mexico, on the White Sands Missile Range, they set off the first atomic weapon. One of my colleagues at New Mexico Tech, who just died, Marv Wilkening, was the last young physicist off the tower. It was his job to screw the last part of the trigger in place. And he said to Dr. Oppenheimer, suppose something goes wrong. And of course, Oppenheimer said, Marv, you will not know about it. Anyhow, I asked Marv, who was a very nice man, I said, how did it work? He said, as you would expect, as you knew it would happen, I put it in and turned it, and the threads were crossed. Backed it out, then he screwed it in and it worked, and he said, I got off that tower because I knew it was on the timer. You had a certain amount of time to get off that tower and head for the bunker. You want to know how bright Enrico Fermi was? They had all kinds of equipment up, transducers and pressure devices to measure the energy released by this nuclear weapon, this great shock wave that would come out of the atomic bomb. He was in a bunker about a half-mile from ground zero, Fermi. Took a sheet of paper and tore it up as confetti, and he waited, and as the shock wave came, he dropped the paper and watched the shock wave move the paper, calculated how far the paper went, deduced the energy in the shock wave, and he was within 5% of the actual value. What I like about this is an experiment that cost 4 cents, and the equipment there probably cost $400,000 to measure the same thing. Anyhow, unfortunately, a month later, and it was a tough decision, and you all know the history, went over Hiroshima and dropped one of these infertile devices and obliterated 80,000 people. It ended the war. The argument pro and con still waxes and wanes, and it's not science. Now, does that mean that we've got it all? No. What's the story? A lot of careful work has been done, and we've finally come to the conclusion, and I'm about to end, which I know will keep you, Terry. I might got 1 minute. Okay, I'm clocked very accurately here. See, at GSci 20, I would say, stay, I've got a test coming. But now I can't do that. I don't have the club. We now know there are 4 forces: the gravitational force, the electromagnetic force, the strong force, and the weak force, which are subatomic forces. Without going into a long story, we have a beautiful theory that explains electromagnetic, weak and strong, and puts them together. But we can't fit gravity into the mix. To this day, the great challenge in science is to come up with a quantum field theory that integrates all of these forces into a single nice idea, like we had with Newton until it went south. We need a new one, and you know what? We're going to find it, we're going to celebrate, and probably in 50 years, some PhD candidate at Penn State will say, it's wrong. And that student may come from New Jersey. Thank you. Yeah. Thank you very much.